All right, hey everyone, I am Paul. I'm going to be talking about the Unison programming language. This work I'm presenting, it's joint work that I've been doing with my colleagues Arya, who's in the audience here, also my colleagues Runar, and a number of awesome open source contributors. So what is Unison? It is an open source, statically typed functional language, very much influenced by a few languages, Haskell, Erlang, and this interesting research language called Frank. Unison itself has been kind of a research project for several years now, but late this summer we started alpha testing our first release. You can help out with that if you're interested, and we're really trying to get Unison to a point where you could use it for real stuff. And so that's very exciting. So why a new programming language? Why another programming language? So overall, the goal, or sort of the guiding philosophy behind Unison is we want to try to make programming more fun, simpler, easier, eliminate needless complexity, and do that by being willing to rethink pretty much anything and everything about how programming currently works. So really just be willing to start from first principles and like rethink things and say like, hey, how do we want this to work? And so that's been kind of the guiding philosophy behind the development of Unison. But early on in the development of Unison, we sort of hit on this one core idea, core technical idea, which I'm going to spend the next 2 slides trying to explain clearly. And this one core idea ends up making so many other things much simpler. So these next 2 slides are like the most important slides of the talk. So, all right. So what's the idea? The idea is that in Unison, we are going to identify code not by its name, but by a hash of its content. So if we have a function factorial of n is the product of the numbers 1 through n, it actually doesn't matter to Unison whether we call that function factorial or whether we call it blah. It also doesn't matter whether we call the parameter to the function n or whether we call it z. We can compute a hash for this, and the hash is j1e ... Now in reality, these are going to be like 512-bit SHA-3 hashes, which I'm not showing the full hashes on these slides. But so the idea is we're identifying the code by a hash of its implementation. And we're also going to store a Unison codebase in a different way. So rather than just storing the codebase as this collection of text files where the text is just this totally unprocessed form of your code, we are going to store it in this more structured way. So we're going to store a serialized syntax tree and associate that with each hash. So the hash of factorial, j1e, we're going to have, say, a subdirectory for that hash, and then underneath that subdirectory, we have this AST file, which is a serialized form of the syntax tree. And then separate from the AST, we have metadata like what's the human readable name or names for this hash. So, okay. Let's take a look at what is in this serialized syntax tree. So this is also important. So if we look at factorial, it's defined in terms of product, range, and plus. And so what's actually stored in the syntax tree is not those names, but the hashes of those definitions. So, and then furthermore, when we compute the hash of factorial, we even normalize away like what the local variables are called, like the parameter to the function and so forth, so those don't impact the hash. And so bottom line, unlike names, a Unison hash uniquely identifies the exact implementation of a definition and pins down all of its dependencies. So it's an unambiguous way of referring to a piece of code that never changes. Okay. So is that pretty clear? I don't know, raise your hands if that was like, if those 2 slides were clear. Okay, I guess I did pretty good. Okay. Okay, great. So So we get all these benefits from this idea, and I'm going to basically spend the rest of the talk kind of going through them and demoing how they work in the current version of Unison. So we get sort of this nice story for doing code-based management, so we don't have builds anymore. You're never waiting around for your code to compile. We can do renames without breaking anything. We can even cache the results of tests, so we don't have to keep running the same unit tests over and over again. And then we also get this nice story for doing refactorings and making changes to our code base without ever breaking anything. So our code base is always going to be in a working state. It's never going to be broken or have, in a state where we can't run things, even when we're in the middle of a refactoring. There's also all these other benefits, which I'm not talking about today, but which are very nice, that also kind of emerge from this core idea. And I gave a talk at Strange Loop a couple months ago that kind of talked through some of these if you're interested. But I'm just going to be focusing on these first two for the rest of this talk. Okay. So let's look at renames first. This is kind of the easiest one. So when we're storing the names as sort of separate metadata, and we're identifying code by the hash, it's pretty easy to just swap out that metadata with something else. So if I want to rename factorial to transmogrify, all I need to do is just swap out that metadata of factorial and replace it with transmogrify. And I'm just updating that information in one place. So I'm not, to do this rename, I'm not modifying a whole bunch of text files and generating this huge diff. I'm really just making that change in one place. And very important is that this rename, it doesn't break anyone. So it's not like the refactoring or the rename that your IDE can do, where it works great, but then if you are a library author and you publish a library and then you later rename some of the definitions, that's going to break all your downstream library users. So renames in Unison sort of don't break anyone, because all the references to definitions like factorial are not by name, they're references by hash. Okay, so we get this nicer story for renames, so that's nice. We also don't really have builds anymore. So when we go to write new code that depends on a definition like factorial that we've already written, once factorial has been parsed and type checked and added to the Unison code base, once it never changes, and we never need to parse or type check it again. We can just look up, hey, what's the type of factorial? So the way that we can do that is just, again, associated with the hash for factorial. We store the syntax tree, but also, hey, what was the type after type checking this hash? And so when we're writing code, Unison really is only ever having to type check the code that we are actively editing at that moment. And it's never having to do like a full rebuild of all the code or anything like that. And also very important is that once anyone has written a definition and added it to the code base, no one else who gets that code needs to parse or type check that again. So this is not just like a compilation cache that's sort of local to your IDE. It's actually part of the Unison code base format. Okay, let's keep going. So we can also cache test results. So most of the time, like you have tests, and the results of those tests are not actually changing. They're deterministic. If it's a test that is not doing I/O or calling out to the outside world. So in Unison, you can actually, when you define unit tests, the results of those unit tests can actually be cached so that you don't have to keep running the same unit tests over and over again. I'll show a demo of how this works. But the basic idea is again, associated with the hash, we store not just the syntax tree and the type, but hey, what was the evaluated result? Was it a passed or failed? And so I guess the actual Unison codebase format is a little more interesting than what I'm showing in these slides, but this is giving you the basic idea of how we can associate different kinds of information with these hashes. And so we're getting all these nice benefits from the fact that the Unison codebase is append only. We never actually mutate definitions in place. So the definition that is associated with the hash never changes. And so we can cache all this information and associate it with the hash, and we don't need to worry about cache invalidation. So certainly your IDE keeps some sort of compilation cache, but it is attempting to maintain that compilation cache while all these text files are being mutated out from under it, which is very complicated. And often the cache, gets out of sync with the files, and you have to like do a clean, and you're like, do I even? Yeah, it's just sort of it can be very, very complicated to maintain that. And so Unison, we just sort of sidestep that. We just have this append-only code base, and we can maintain all these caches, and they're always just correct. So, all right, I'm going to show scary. We're going to actually do a live demo, and we'll see how this goes. But before, I just like holy crap! Like it's like we've discovered this alternate reality of self-consistent alternate reality of programming, where we sort of are getting all these things kind of for free that are just emerging from this one idea. So I thought that was cool, and it was something that made Unison very fun to work on. Okay, so I'm going to switch to a live demo, and we'll see how this goes. Okay, so on the right-hand side, I have my text editor, Vim. You can use whatever text editor you want. And on the left-hand side, I have Unison, which is watching for changes to my text file here. Or specifically, any file that ends in .u. And so every time I save this file, Unison will notice and will parse and type check the file. If there's errors, it'll tell me about errors. And so you can see it picked up the definitions of factorial and product. Maybe while I was writing this, I wanted to look up a definition, like, oh, I wanted to call like a list function, but I wasn't sure which one. I might do a find. I get tab complete. I might look for a definition like range. I might look for a definition like map. And I might view the code. So I might just sort of interactively be querying the code base for different things, just as I'm writing the code. And but okay, so another thing that we can do in these .u files, so we call them scratch files because even though you're editing the code, but in a text file, but they're just sort of, the text files are just sort of this temporary way of sort of entering in or viewing code, but you don't really keep them around, as we'll see. So another thing you can do in scratch files is just interactively evaluate expressions. So any line that starts with greater than, we call that a watch expression. It gets evaluated on every file save. The evaluation is just sort of incremental. It only sort of recomputes things that are necessary. So if you see this, I don't know if you can see this, but if it's a red arrow, that means it actually had to compute it because it wasn't in the evaluation cache. If it's a gray arrow, it means that it was already in the evaluation cache and it just looked it up. So it's pretty smart about sort of only recomputing things that have changed in your scratch file. I guess the other thing I was going to show is that it pretty prints these evaluation results, so you don't have to worry about formatting them to look nice. It sort of formats them based on available width, which is nice. And what else can we do? So we can actually write our unit tests directly in our scratch file as well. So here I'm just checking a few examples of factorial. This is called a test watch expression. And we can see that it is passed. And it also says, hey, this was cached. I found it in the evaluation cache. Why is it cached? It's cached because I just ran through this example earlier. Okay, but and so once I've written the code and made sure it works, maybe written some tests, I'm happy with it, and now I'm like, okay, great, I'm ready to add it to the code base. So if we look at this message, it says these new definitions are okay to add. So I'm going to go ahead and type add. And now these definitions are in the code base. So we can view them. We can, if we do a find for factorial, it auto-completes, so the code base has sort of recognized that this is a new definition, and it can find it, and you can query for it. And I'm actually, now that the code is like in the code base, and I can sort of get it back at any time, I'm even just gonna like delete that stuff from my Scratch file and just keep it nice and tidy. If I wanted to get factorial back, like say I want to make changes to it, I just type edit, it pops it or pushes it back onto the top of my Scratch file. I might do some editing, but I'm actually, it's cool. I'm happy that it's there, then I can get it back at any time, and so I'm just going to leave it there. So another thing so once the code has been slurped up into the code base like this, if we do things like rename, like say we rename list.foldL to something something, and we view the definition of factorial again, the definition of product again, which uses foldL, you can see it picks up that new name for what used to be called foldL. And this also works for, so I'll actually, let's undo that because old name is better. But this also works for when you write documentation in Unison. So Unison documentation, it's actually represented as values in the Unison language. So you can even like build up documentation programmatically. But here I'll just show like a little example of, this is some documentation for product. You basically write your documentation in Markdown. You can have these links which start with an @ you can splice in a source as part of your documentation. You can do all kinds of neat things. And when we view the documentation, these are actually links to the definitions. And so if I were to do that rename again, and then view the documentation, it picks up the new name. So your documentation links are never broken. It's not just like text files that like gets out of date. You actually have links that are by hash, and that when the docs are displayed, they pick up the latest names for things. Okay, let's go ahead and undo that change again. And cool. So the other thing I was going to show is, okay, when I run the tests, so there's a test command. You can see it's like, okay, here are the cached test results. I didn't actually need to run anything. I'm just looking up these test results from the test cache. You could blow away your test cache at any time, and it would recompute. But generally, you don't have to like keep running the same tests over and over again. Okay, cool. So, and that test cache, I guess that works even if we say rename. If we rename factorial to something else, the test cache isn't impacted because the test cache is keyed by these hashes. Okay, I'll go ahead and undo that. All right, so that's kind of showing the basics of kind of how you edit and interact with the Unison codebase. And it's kind of sort of a low-tech, minimal environment. You really just have like one text buffer and Unison running in a terminal. And that's all you need to be able to write Unison code. Okay, so let's jump back to the slides. So there's this big question of like, okay, in Unison, definitions, they don't change, right? If we factorial, it has some hash. If we change the definition of factorial, if we say factorial then is 42, we're actually just introducing a new definition with a new hash, which coincidentally is just also called factorial. And so all the code that references factorial is referencing it by hash, and so it's still by default referencing the old hash. And so this raises this question of, well, how do we actually refactor code in the Unison world? And this is something we had to figure out a nice way to do. So how does it work right now? So the way it works right now is we just modify code in place, right? And that works pretty well when we're making a type preserving change. So you're not changing any type signatures, just changing an implementation. You get that one definition compiling, and your code base works, and it's all good, right? Okay, but then we have these other changes that we're often making which are not type preserving. And then we make the change, and then we get a bunch of compile errors. And our code base is basically in this broken state. And we're like, okay, great. I'll just kind of work through the compile errors, and it's all good. I can do this. You get it down, and you finally maybe feel a little bit like a robot because you're kind of like reading through these confusing compile errors, and you have to sometimes you don't even read the compile errors because they're just so misleading. You're like, you know what? I'm just going to look at what line it's pointing to and see if I can figure it out. But you're almost back to having a working code base, so you're like, okay, I can do this, and I'm okay. And then you fix that last error, and there's like 37 more errors. And you're like, what? Okay, what's even happening here? That initial list of 22 errors was maybe misleading. It was maybe covering up other parts of your code, preventing other parts of your code from even being examined by the compiler. And you're like, oh, okay, 37 more errors. All right, I guess I can do this. It's okay, breathe, work through this, 37 errors, that's not that many. And so you work, and you finally get it down to that last error, and you finally fix it, and then there's 26 more errors or something, and you're like, what's even happening here? Am I even making any progress at all? I'm just sometimes the number of errors is going up, sometimes it's going down, sometimes it's going left, right, sideways. I feel like I'm adrift in this sea of errors, and just, I don't even know if the information that I'm getting back from the compiler is even accurate in any way. And a lot of times, I don't know if this has ever happened to anyone, you might be hours into this long refactoring, and then you realize, you have this terrible realization that the refactoring that you're working on is it's not even correct. It's not even going to work. And it wasn't until you slogged through hundreds of confusing compile errors that you were able to realize you know what, this was just the wrong approach. And you're just you're totally demoralized, and you're just forget getting anything done the rest of the day because you're just spent. All right, anyone, does that resonate with anyone? All right, great. All right, so let's not do that. But what's actually going on here? So it's if your code base is like a skyscraper, and you're trying to go from version 1 of the skyscraper to version 2 of the skyscraper, the way we modify a code base right now is we're yeah, let me just try to modify the skyscraper in place. We'll just pull out this one little foundational column, and it collapses into this pile of rubble / compile errors, and then you attempt to reconstitute a standing skyscraper from the rubble. So we're not going to do that in Unison. Instead, we're going to build a new structure off to the side. And this is just like what we do with a functional data structure. We don't actually mutate a functional data structure. We create a new version of the structure that shares a lot of the same content as the existing structure. And we're going to do the same thing for our code base. So here's an example. We have Thanksgiving dessert, depends on pecan pie, pumpkin pie. Both the pies depend on pie crust, and pumpkin pie depends on pumpkin filling. And so what we're going to do is, like, if we want to introduce, a new and improved version of Pumpkin Pie, is we are going to just do that off to the side. It can still share the same, it can still depend on pie crust and pumpkin filling, so we don't need to make copies of that. And we can just incrementally build up this new versions of things off to the side. And so the idea is that we have an existing code base, and then we have this incomplete but also still working code base that we're building up off to the side. And at the entire time, we're going to keep the code compiling. We're not going to have anything broken. We're going to be able to do other things, and it's going to be great. All right. You ready for a demo? All right. Let's see how this actually works. OK, so I'm going to do a you can do a type-based search in Unison. So I'm just doing a search for what are all the things of type ingredients. And maybe I want to look at some of these. There's my pecan pie and pumpkin pie. And we're going to do a refactoring, and we're going to edit pumpkin pie. And OK, I guess the first change I'm going to make is like a very straightforward one. I'm going to make just a local type preserving change. Like, let's increase the amount of pumpkin spices from 1 units to 11 units, whatever that means. All right, so we'll kick it up a notch here with the pumpkin spices. OK, so we get this type checking, and I'll go ahead and type update. And Unison tells me that, great, I've updated this definition. You don't have any refactorings that are in progress, because basically I've been able to propagate that change automatically for you. So if we look at what's happened here, so it's actually recorded this change in what's called a patch. And the patch is basically a mapping from old hash to new hash. And so we can see that the patch contains this mapping from, this was the old hash of pumpkin pie, and now it's being mapped to the current new version of pumpkin pie. And if we view the definition of pumpkin pie, we can see that, yeah, it's picked up that new amount of pumpkin spices. OK, so that's kind of the simple case of you're just editing a code, it's type preserving, and it's sort of just as much work or just as little work as it is right now when you're just modifying things in place. So I think the power of this approach comes when you are making changes that are not type preserving. So I'm actually just going to undo that change. So let's make a change like adding a parameter to pumpkin pie. So I'm going to actually make it parameterized on the type or on the pie crust. And you can see it picks up that new type. And now if I do an update, so it's not going to know how to, so let's look at one of the dependents of pumpkin pie, Thanksgiving dessert. It's not going to know how to update that dependent for me. So I'm going to need to tell it how to do that update. So let's see how this works. So I type update, and rather than it sort of presenting me with like a list of compile errors that I have to work through, it is just telling me like, here are some definitions that I don't know how to update yet. And I recommend that you work on them in dependency order. So I might type, and actually I'm running out of time, but I'll just show this very quickly. What I'll actually do is I'll change this to, I'm actually just going to bind that dependency right here. So I've added the parameter to pumpkin pie, and here I'm just binding that parameter. And so this makes Thanksgiving dessert. I'm preserving the type of Thanksgiving dessert. And so any dependence of that can just be updated automatically. And so if I type update, you can see I don't have anything left to do. The refactoring is complete. And it's all good. Now, if at any time during this refactoring I had some other work I needed to do, I wanted to like evaluate some other code or introduce some new definitions, I could do that. Having a refactoring that's partially completed doesn't prevent you from doing other things. Your code base is not broken. So yeah, that's kind of the basics of how you can sort of make changes to your code base in this very structured, controlled way, and without having this big list of compile errors. So great. If you are interested in this stuff, we are currently alpha testing Unison. If you'd like to help us with that, test it out, report bugs, like tell us what you think could be better. unisonweb.org/docs to get started. We also have a Slack channel, for like asking questions and things like that. And also, if you just want to follow along with the project, we are on Twitter and we have a blog. And just again, thank you to all of our open source contributors. And also, we have lots of open source work and different projects. So if people are interested in contributing to Unison, come find one of us after, and we'd be happy to chat. So thank you.